All right, I guess we'll get started. I'll give a brief recap to remind us where we were yesterday. The story has been using monads in various ways to give semantics to programming languages, and then use the equational theory of monads and augmented perhaps with particular equations to the event given by the, or induced by the event handlers for particular kinds of effects like state effects, to reason about the equivalence of programs. And so we've seen how to do this yesterday for sort of IMP, where we started with concrete algebraic data type for the abstract syntax, sort of interpret that into a representation as I-trees, which in some sense factors out the control flow, but leaves these memory events. And then we can install a memory event handler to implement those read and write events. And that will yield sort of computations in this state transformer monad, where we have functions from memories to potentially diverging functions that produce memories as a result. And the nice thing about this is we can reason at the different levels of abstraction depending on the needs. And so we went through a long laundry list. In fact, Ali pointed out, I think I said something incorrect yesterday when I was explaining these two slides. So these slides are, this is sort of a list of facts that are true regardless of the memory model. So these are semantics of IMP, of IMP programs. These are, each one of these lines is an equivalence that you can prove regardless of how you implement the memory events. So for example, no matter what you do with the memory operations, IMP commands will be associative and this way, and you can eliminate skips and so on. And you can even do some things like unroll a while loop. Intuitively, this particular version, whatever effects are in C, well, you're going to run them the appropriate number of times, both before and after. And so it doesn't matter what the read and write events do, they're still equivalent. Whereas these rules, you do have to justify based on the memory model, right? So for example, the fact that we can turn a while loop where we have events there into a while true into, we can eliminate the command. Well, this will hold only if we've completely handled all the memory. Good, so we've been able to sort of lift our reasoning, and then at the end of last time I showed you that we can sort of prove a bunch of, prove these equivalences and then use them to do various optimizations for things like constant folding, where we can prove some arithmetic expressions. And at the end of class, we sort of saw, well, we can implement a syntactic transformation. In this case, it's folding constants that just takes an arithmetic expression and produces an arithmetic expression. And then we could prove that it's equivalent, that it's sound by using our notion of equivalence. And the proof ends up being fairly simple by just rewriting according to those rules that we saw. And we can do the similar thing for commands. So this is just doing constant folding over commands, kind of very classic compiler optimizations and so on. So that's kind of where we left off yesterday. Any questions about that idea so far? So what we've seen, this is just an example of using constant folding, where, for instance, we can constant fold this 4 plus 5 into 9, and the proof is actually just use our soundness proof of the constant folding. Yeah, question.
Could you maybe just give some intuition why the two programs that you've shown need the memory model to be justified?
Why these two do? This one. That's a good question. I think maybe this is true. Let me look at them again. So, oops, where is it? Back here. Let me think about this. No, I think actually now that I think about it, these are true regardless of the memory model, because we're not actually using any of the equations on the state. Yeah, another question. Yeah, sorry. Yes. Yes, I'm too close to the board, and Ali did point this out. So if C has a side effect on the memory, well, this program is going to go into an infinite loop. Yeah, so we do have to interpret the memory model for this. I'm getting myself confused because it's 9 a.m. Right, so why is this? Well, okay, why do we need to interpret the events in the memory model here? So if we didn't, this one would be intuitively a tree that is infinitely big, and let's say that there's a write to memory. So it's like while true, do x gets 1. Then that would be an infinite tree where we have a write to x, write to x, write to x forever. And that's clearly not true, not equivalent to this. In fact, you can prove that this one, the denotation is just the all tals tree. So a tree that has all tals and a tree that has writes events are not weak or strong bisimilar. They're just different. But once we interpret them, interpret the events, both of these are going to be functions of the form, give me an initial memory, and then I will return the I tree that has all tals. So it will go into spin. And it will never produce the final memory. But both of those trees will now be the same. Or once you've applied them to initial memories, you'll get the same tree. And so we do have to interpret the memory events in order to justify these two equations. Yeah, sorry.
On that note, can you show us the conditions of the proof for right counter?
For which one?
Or I guess for while true.
For while true, do C? Sorry.
Yeah, like wherever it's true.
Oh, where is this true? So that would be this one, right? Yeah, this one right here. That's the whole proof. So while true, do C is equivalent to while true, do skip. I mean, there's some lemmas, but basically it's one of these loop unrolling, and we have to do it in the, this interp state bind means that we're doing our interpretation in the state monad. There's a helper function that basically sets up the invariant that we can keep making progress. You can look at the full Coq development if you want to see what those look like, but the proofs aren't that complicated once you get to this level.
In terms of the method.
Yes, this particular one is after interpretation into the memory model. Good. Any other questions? All right, so what I would like to do, so that was proving equivalences of IMP programs under various conditions. But I claimed at the beginning that we can use this sort of monadic structure to do other kinds of reasoning. So what if we wanted to, for example, prove, we have a particular program and we wanted to prove some fact about it. And the way we might do that in a traditional program verification approach would be to use something like a Hoare logic, or maybe if we're fancier, a kind of separation logic or concurrent separation logic and so on. So I want to show you how we can use these monadic semantics to justify the soundness of such a logic so that we could do proofs about, say, functional correctness of IMP programs. And the trick is actually going to be, remember, we introduced this notion of EQM, which is just this type class or this way of saying that, whenever we have monadic computations, we have to spell out what it means for them to be equivalent. And we had this, this predicate that we talked about, and we proved the monad laws up to EQM, which for I trees is weak by simulation, typically. And we're going to make one tiny tweak to allow us to do sort of relational reasoning about proofs, and that is to allow us to relate two monadic computations that just happen to have different return types. So the only difference is here we're just saying we're going to relate two programs that have the same return value, and here we're just going to relate two different return types. You could imagine if you're trying to prove a relational property that you're, say, suppose your language has Booleans and integers, and you might want to show that if you convert Booleans to so that true is related to 1 and false is related to 0, you could kind of make a program transformation that does the same thing morally but has a different representation of the values. So you could relate Boolean and int, for instance. Okay, so we'll call this EQMR. It's a type class that looks like this. It's really just a little bit of notation and some more type classes, but we'll call this heterogeneous relations, just to give us an abstraction. But it's basically arbitrary binary predicates on two different types. So it's just a relation on A and B. And then we'll say that EQMR, basically what is that? Well, it's parameterized by one of these heterogeneous relations on the return types, and it lifts it to a relation on the monadic computation type. So this is really just given a relation on the return values, how does your monad consider them to be equivalent? And for I trees, basically the intuition is that we're going to use either strong or weak bisimulation. And the only difference with what we've seen before is that rather than when we get down to the leaves, requiring them to be equal, we'll just require the leaves to be related by this R predicate. So that's really it's the same definition. In fact, this is the more primitive notion that we use in our library, is this binary relation on trees parameterized by the result relation. Just to give you a very concrete example, and I'll write this notation kind of our weak bisimilarity parameterized by or indexed by the relation type R. And I'll give you some more intuition about this over time. But basically, here's a very concrete I tree where we have, say, a read event for the for the location X. And then in the leaves, we just return the value that's read. So this tree looks like it has a single node at the top, read, and then there's an infinitely wide branch of natural numbers. For each leaf, we just return that natural number. This one is very similar, except that I'm returning 1 plus n. So these are not either weakly bisimilar or strongly bisimilar because they return different things in the leaves. But if we allow less than as the comparison, for every leaf here, the corresponding leaf over there is less than. And so this would be an example of this EQMR. Yeah?
When you have this relation like less than, you're requiring the same shape of the tree.
That's right. So so the comment was the same shape of the tree. Well, up to tau, right? So we're going to ignore tau's in the way we talked about last time. But basically, when you get to the kind of corresponding leaves, we'll just require them to be lined up with R. Yeah? Relation H and rel H. Where is relation H? Oh, yeah, that's my typo. Rel H, rel H and relation H. In fact, maybe I need to refresh. I was trying to make this, so you could read this as relation H. This is my typo in the comments. They're the same thing. They're the heterogeneous relation. And just as an observation, if we instantiate R with Cox equality, then that degenerates back to the old version of bisimulation that we saw before. So this is what we actually provide in the library. Good. OK, so here's some intuition. You can kind of think of R as a predicate on the leaves of these trees, right? And in some ways, you remember from Amal, she may have mentioned something called the fundamental theorem of logical relations, where you have a term related to itself at the logical relation type. Well, if we consider that case here, right, so that's going to force R to be a predicate on this homogeneous predicate. So it'll be A to prop. We're going to have to look at the same type on both sides, because we're trying to compare to the same tree to itself. But if you think about what this is, it's sort of a predicate on the leaves of the tree. And if we think of which values would be related to themselves in this predicate, that's a bit like a postcondition. Right? So it's saying that after you run this monadic computation, you get to some leaf. That leaf is going to be related to itself by R. And we can actually formalize that intuition and think of these as a postcondition on the computations of a monad. And this type class, EQMR, is kind of a generalization of that. OK, so as an example, you'll remember that when I introduced bind and we had return, we had to have these properness lemmas. These are sort of the logical relations that show that they're respecting the equivalence. So here is what the logical relation for R looks like, for ret. It basically says the return constructor of an I tree will be related to some other return constructor. So we're returning R1 in this case and R2 in this case at the relation RR if and only if those two values at the leaves are indeed related by that relation. So this is just a fancy way of saying that these leaves line up according to this predicate R. That's the logical relation for return. Then, of course, we also need the logical relation for bind, and here it is in its full gory detail. It has to quantify over quite a few things. So let me work from the bottom up. So we're trying to show when are two computations logically related, if they're both binds. Well, if we think of RR as a postcondition of sort of the entire computation, you can intuitively think of, well, the bind is going to find some postcondition of T1 and T2 under which the continuations yield related trees that satisfy related postconditions for the whole computation. So this is sort of breaking, if we're trying to break a big computation down into an initial part which is given by T1 on one side and T2 on the other, it suffices to find a way to relate T1 and T2 with some postcondition, and then for all of those cases where they're related, relate the continuations with the overall postcondition. And that's literally what these spell out. So we have T1 and T2 have to be related at some postcondition. I'm calling it UU here. We can think of the types U1 and U2 as sort of the intermediate return types of the two trees, as sort of the intermediate state that we're allowed to mention in our sequential composition. And so the continuations will consume those things. And so really what we're doing here is building a logical relation that says, if we have these sort of prefix computations whose postcondition is UU, then, and we can guarantee that for our two continuations, K1 and K2, when they're given inputs that satisfy the postcondition of the prefix, they give us related results. Then we can compose all of that together. And if you squint at this, this is basically the sequence rule from Hoare logic, but kind of expressed monadically rather than kind of statefully. But that intuition we can actually turn into a real definition. So with imp, for example, we'll be able to use essentially these logical relations and these EQMR with the postconditions to encode the semantics of something like a Hoare logic. Okay, so this is a big, this is a wall of text. Are there any questions about this? This is, if you look at the type of bind, this is just a pretty general version of the logical relation for bind. Yeah.
So by Hoare logic, you mean like unary Hoare logic? Or
yeah, well, so the question is unary Hoare logic. And the nice, so we'll see that. So I'll implement unary Hoare logic, but this also will work for relational Hoare logic as well. So it generalizes both. And I'll actually show you an example of both of those, although I won't go and develop the full binary relational Hoare logic because it's a little bit much. But yeah, you can use this for unary Hoare logic or relational Hoare logic. Is another comment or? Great. Okay, so let's see how that works actually. But before we do that, there's some properties that we expect to hold of this type class that tells us how to lift sort of postconditions on computations to relations over monadic computations. So we expect it to be sort of well behaved in the sense that, well, if our relation on the leaves is an equivalence relation, then so is the lifting into the monadic computation. And it should be monotonic in the sense that, if we have some refinement of a relation, then lifting it to the computations is also monotonic in that way. And as an aside here, I'll say there's some quite neat things that you can do with this sort of notion of self-related values, you can define something called the image of a monadic computation, which you can think of as, if you unpack the definition, it basically says it's the strongest postcondition you can give for a particular monadic computation M. And another intuition is, what's the strongest postcondition? It's exactly the things that might be returned by that monadic computation. So for a sequential program, you can think of it, the image, as just the value you're going to get out at the end. But if you have some kind of non-determinism in your, like in an I tree, the image of an I tree is all of the, it holds exactly if there's a value at one of the leaves of the I tree. So it's kind of a nice definition. And so you can, if you think of a monad as kind of a generalized container where the leaves tell you what's in the container, the image of M tells you that, you know, one of the leaves contains the value A. So it's sort of like the inclusion. Okay, so that's some intuitions. And here is how we can define the unary or logical definition. So we're going to define, ultimately, we're going to define a very standard kind of Hoare logic where we have some imp computation C is command C, and it's there's some predicate on states P and Q, and P is the precondition and Q is the postcondition for our logic. And P and Q for imp, what is the predicate? Well, it's a predicate about the memory of the imp program. So, you know, we might have a predicate that says, you know, the precondition is x is greater than 0, and the postcondition is that y is equal to x plus 3 or something like that. And so imp-style Hoare logic assertions are just predicates on the memory. And now we can define the meaning of a Hoare triple using this unary predicate. It's basically saying that, well, give me the state, the initial state, sigma, assuming that the precondition holds of that state, then the command C is related to itself. So this is why it's a unary Hoare logic and not a relational Hoare logic. We have the same command on both sides. If we run them in that state, they are related with a postcondition that says that, well, they're going to produce two, I know this computation is going to produce some final state sigma 1. This computation is going to compute some final state sigma 2. For the unary version of this, those have to be the same because we're talking about the same command. This actually encodes, in some sense, that imp is deterministic. This would not necessarily be true if we had non-determinism in imp, and then we would have a different notion of the Hoare logic soundness. But for deterministic imp, this requirement is basically going to force us to prove that the semantics is deterministic, which is how we justify our reasoning principles. And then we also just say that, oh, because they're in the same state, the postcondition is satisfied. And if you think about what this means from a kind of I-tree point of view, this is the classic Hoare logic, which is called partial correctness, meaning that if C goes into an infinite loop, then any postcondition is true. And intuitively, why is that? Well, this equivalence holds only for the reachable leaves, right? If the C goes into an infinite diverging program, then we'll never get to the postcondition. And so, but that's what you want for classic sort of Hoare logic triples. Okay, so this is the meaning of a Hoare logic triple for imp. Any questions about that? Once we defined it semantically, now we can go through the exercise of proving inference rules for reasoning about programs. And here you can just take the standard collection of imp-style Hoare logic rules as found in, say, Software Foundations in the earlier part where they do all of this for relational operational semantics, and they give a soundness proof in terms of the small step imp semantics. We can recapitulate the soundness proof, but with I-trees using this relation. So, for example, here is the classic rule for skip. And here stating these basically as theorems in Coq. So we're proving the soundness of our logic by just stating, well, P, if the precondition P holds and you run skip, then the postcondition P is true. And the proof is actually really quite simple. It's just unfold the definition and look at the things. So here is the sequencing rule for imp. So you can read these as the premises of the inference rule, and this is the conclusion. And you'll notice that it's the classic, if you can find a postcondition Q of C1, so that if you start from precondition P and run C1, you end up in Q, and from Q you can get to R via C2, well then you can sequentially compose them to get from P to R. Again, this actually just follows from, this is not a great name, but this EUTT-CLO-bind, for various historical reasons, is the name of the lemma in the iTrees library that corresponds to this logical relation. So it's just a use of this sequential composition rule packaged up for imp, okay? And we can keep going. So I'm not going to dwell too much on this. It's like a standard exercise to just prove each rule of Hoare logic sounds. So there's a couple different ways of treating assignment. So here's one. This is how you would often see the assignment rule. So if we're going to update the variable x to some arithmetic expression a, well, the precondition is that, well, the postcondition Q holds if the precondition is Q where we assume that x is updated to a. So this is a way of saying that this assignment effectively modifies Q to have, we can assume that x is type A. Here's another variant that's a little bit easier for forward reasoning. So if we start in some precondition P and run the same assignment, so this is a different rule, it's also sound. Well, what does that mean? Well, it means that there exists some final state where we evaluated there exists some initial state where we evaluated A in the initial state, and then we update X to be that. And the resulting state, the predicate is that sigma, the final state here, is what we get by doing that update. And then also, the precondition must have held of the initial state. So this is just saying that sigma prime here is the state that we assume satisfies P. And if we start in that state, well, then we get to some place where we've updated the memory to have X maps to A. And you can, here's the classic if rule where we have the true branch and the false branch, and we sort of conjoin the fact that we learned that B is true as a precondition for C1, and not B must hold for C2, and so on. And we can also prove the classic while rule. So this is, if P here acts as a kind of loop invariant, if that's preserved across the body of the loop, assuming that the Boolean guard is true, well, then we know that P will hold after the loop if it terminates, and moreover, we'll know that B is false. So these are just very standard textbook rules. Question?
In the definition of the Hoare triple, you said
Yeah.
that this wouldn't work for non-determinism, but I don't know exactly how you add non-determinism to iTrees.
Yeah.
But it seems that here you're really comparing the two iTrees, right?
We're comparing, so this is after state interpretation. So we're comparing functions from imp memories that return essentially fully interpreted, so delay of memory. So the only iTree component here is really just the possible infinite taus. And that's because imp is deterministic. If we had multiple, if we wanted to have non-determinism, we would have to have encode a set of possible answers in some way. But then this would not be a valid way to encode these rules because we might end up with different states running the same command.
If you encoded non-determinism as maybe branching.
Yep. Yeah, so we could do that. So, well, okay, so this is actually a good question. So you might imagine the thought experiment of let's add non-determinism to imp. Let's encode it as an event in iTrees as maybe a new kind of event. Let's call it choose or something like that. That gives you a non-deterministic choice of two branches. You could have those. The question is, do you interpret away those events? In general, if you have those events in your I trees, then probably you don't want just structural equivalence, because I would say that the sort of associativity of those choice events would affect the shape of the tree. And in that case, both strong and weak bisimulation, if you leave those events in the tree, would be probably too strong. It would be too fine for what you would really mean as the equivalence over non-determinism. But what you could do is you could write a handler that interprets those non-deterministic events into some other monadic domain, maybe predicates on whether you can reach them, for instance. And then that would induce the appropriate notion of equivalence. So you would quotient out by more equations that would basically say, one way of associating the choices would be equivalent to another way. You can definitely do that with plain I trees, but that reasoning actually gets a little bit complicated, which is the motivation for some follow-on work that we've done called choice trees, which basically bake that notion of choice in and build an equational theory that kind of treats that specially, so you don't have to do this extra level of interpretation. But yeah, so I guess, does that answer your question? Yeah, good. So I guess we're proving the determinacy of imp commands by using this formulation of things. Good.
Can
So,
I
sure.
ask a question? You go back a slide.
Yeah.
So
Or-
Boolean expressions here really are the syntax. So you're doing some kind of.
Yeah, so this is a software, you're saying, can we use B here as a precondition and as a piece of syntax?
So you're lifting and.
Yeah, so
maps, right?
yeah. So this is a good observation. So this is a trick that that Software Foundations does, which is basically this piece of syntax is overloaded, both as a abstract syntax, like x equals y would be a piece of abstract syntax, but also as a predicate on state. And it's actually handled kind of transparently through yet another type class that sort of interprets the Boolean into predicates. So you can write very natural looking things. But that's sort of, but there is a little bit of a, and even and here, right? This is a lifting propositional and to and over state predicates. So there's sort of a bit of notational magic going on here. Yeah.
A related question on the previous slide. What are the assertions P, and how are you able to replace X with A?
Yeah. So really, in Software Foundations, the assertions are literally just defined like this. And then this notion of like the assignment here, where you can do an update here. This expands into a predicate where you assert that X equals A and so on. So there's sort of there is some magic being hidden by the notation that lifts this update to the appropriate state predicate. Yeah.
So related to the question before, so you mentioned that if we use like choice as the event, then like some equational theory wouldn't work out.
That's
Can we
right.
specify the equational theory of choice inside of E as something
Right.
like that way?
So the question is, if we add new events like choice, can we kind of impose or specify after the fact an equational theory? And I think maybe we thought a little, so I would say the way I like to do that instead is to give an interpretation of those events into a semantic domain that justifies the equational theory, the way we've done with memory events. You might like to instead just say, these two events satisfy some equation, like some associativity law for choice. I don't know if that's impossible, but we haven't pursued that. So this would be sort of like imposing an equational theory and kind of quotienting by another equivalence relation after the fact. I don't quite know how to do that for I-trees, but it's a good thought. Good. Okay, and so we can keep playing this game. So these are the rules for logical consequence, various instances of it, so you can sort of strengthen. You can strengthen the precondition and weaken the postcondition and that sort of thing. So these are all classic Hoare logic rules. And you can have, there are various kinds of vacuous assertions. So logically, if a predicate holds for any state, this is sort of the true of the memory predicate semantics. Well, that's a valid post condition for any command, and sort of false is also a valid precondition for any command. So good. The other thing that you can get, though, which is quite nice, is that these semantics satisfy, they preserve, well, the equational theory that we already wrote for imp. So what this says is if we have, some pre and post condition that we've proven for C1, and we can, assuming the precondition P, we can prove the equivalence with C1 and C2, well, in fact, we can rewrite C1 to C2 and preserve the reasoning that we did. This is quite nice because now you can imagine, rewriting C1 to C2 with an arbitrarily, you could use your optimizations to prove, in fact, this rule composed with the various optimizations we've already seen says that your optimizations preserve your Hoare logic reasoning. And so, those program transformations won't affect any correctness arguments that you've made. So that's quite nice. And in fact, the proof of this is really very pleasingly simple. It's just unfolding the definitions and using essentially transitivity. And so, you can then use these Hoare rules either automated or not, or manually to construct proofs of various things. This is just a tiny example. So in in any starting state, if we check whether x is 0 and then run a command on y, we'll end up in a state where x is less than y. And you could build a little theorem prover to try to search for this, but you could also just apply these Hoare rules of reasoning in this kind of this style to prove this fact about this particular program. Good. Okay, so that's cool. And this is, as someone mentioned earlier, kind of a unary predicate. I wanted to just show you very briefly how you could do relational reasoning, so where the commands aren't the same on both sides. And this would be very useful for showing various kinds of optimizations or program transformations. And here's just a kind of toy example that is maybe a little bit contrived, but it illustrates the point. So suppose we have this command, command 1, and another command, command 2. They're very similar, except that I've swapped x and y between them. So on imp states, whatever we do to x up here, we do to y down there, and vice versa.
Can you make the font a little bigger?
Oh, yeah, sure. I can make the font bigger. So these are two commands, and we want to prove that these might be related, but of course, they're not related for any input memories. They're only related for the ones where we sort of permute the x and y's in a sensible way. So we could define a kind of relational invariant that says, if we've swapped x and y, we'll relate memory sigma 1 to sigma 2 in this way. So sigma 1 of x has to be sigma 2 of y and vice versa. So these two clauses say that we've swapped the meaning of x and y. And this just says for anything that's not x or y, they agree. So this is a pretty strong relational invariant that just says we've exactly swapped the meaning of x and y in these two programs. And now we can use our equivalence up to sort of our relational equivalence to just say this is now not a precondition on a single memory, right? This is a precondition on two initial states, sigma 1 and sigma 2, where we know that we've swapped x and y. And we can now prove that command 1 is equivalent to command 2 with a postcondition that says, well, we've still swapped x and y, and actually the unit is the same. So this prod rel here creeps in because I sort of hid it in the Hoare logic version, but remember the meaning of a command is a memory to memory cross unit computation because commands only return unit in the monad. So this prod rel here is saying, the memory component has swapped the x and y's, this EQ is just saying the trivial unit value that we get out of the computation is just related to itself. And so we could do a little proof of this relational correctness fact. But this basic idea of doing a relational reasoning between programs can scale up. So let me just, I wanted to show, so at the beginning of the class, I showed how to optimize factorial by doing loop unrolling and constant folding and all this sort of stuff. So here is a piece of the code that you might need to do to implement such an optimization, right? So, so this is substituting, this is a substitution operation. So this is just a piece of, it's all manipulating syntax. So the idea is that we have some variable x, and we want to replace all occurrences of x by some other expression, ax, inside of a. So this is really just a kind of standard substitution. So as an example, if we substitute y plus 2 for x in this expression, x plus z, well, then we better get y plus 2 plus z. So it's just a substitution operation. And this is just a program that works over the abstract syntax. So, and the only interesting case is the variable case. So if we found x, then we just put in the thing we're substituting, and otherwise we leave it alone. And the rest of the code is just recursively crawling over the abstract syntax tree. Okay, so this is a piece of what you might implement as a compiler or some kind of optimizer for imp programs. And we can specify a correctness lemma that says something along the lines of, for any initial state sigma, if the meaning of the variable x in the state sigma is equivalent to the meaning of the thing we're substituting for x, ax, well then the original expression is going to have the same meaning as the substituted version. So this is just the correctness of the substitution operator, assuming that we are substituting equivalent to x in the original memory. Yeah, question. This also depends on the memory model, and also this also relies on the fact that imp arithmetic expressions are pure, right? So this also asserts that, in some sense, that the meaning of ax can't change over time when we do this. Oops. Good. So that's a correctness lemma, and then we could do a similar kind of thing. So this is the code. Oops, sorry. That is the similar sort of function that does exactly the same thing in a command. Of course, naively substituting an expression inside of an imp command is not sound in general, because imp can update the value of a variable inside of the thing we're substituting, or it could update x. And so in a real compiler, you would do some kind of data flow analysis or some kind of program analysis to figure out when you're allowed to substitute. Here, I sort of did an expedient hack that said, OK, the result of this is going to be a command plus a Boolean flag that is true if either the value of x or the value of ax changed by the command, and false otherwise. So it's sort of building together a little bit of program analysis with the substitution operation, just to so I didn't have to spend too many things proving an analysis correct and then substitution given the analysis. So just as an example, skip substitution does nothing on it, and it doesn't affect the value of x or ax, and so that's fine. Here's if we have an assignment, what we do is we want to call our arithmetic substitution operation on the right-hand side of the assignment. And let's call that A prime. And then we need to, so that's going to be the result of our substitution. We have to also indicate whether we sort of mutated either x or the meaning of ax. So that could be problematic if either x is equal to y, so we've sort of affected x by this assignment, or if the thing we're substituting mentions y itself, then this is going to be unsound in general. We're sort of this update to y is going to change the meaning of ax, so it wouldn't be sound. And so this is sort of the analysis that tells us whether our substitution is correct or not. And we can kind of plumb this through. It's a little bit of, so intuitively, let me show you the example. I think it's maybe clearer here. So if we start with an imp program like this that has a bunch of assignments to variables and we want to replace x by 0, well, I didn't. So this one, it's OK to substitute x because it's never affected. We don't update x anywhere. And of course, 0 is a constant. So this one, we could replace all the x's by 0. And then under the assumption that x was equivalent to 0 to begin with, that would be a sound substitution. Whereas here, x gets changed to be 3 right away. So we couldn't replace the x's by 0 in this program. It's imperative. OK. So all that to say, we can prove a more complicated than our binary relation for swapping variables. We can prove the correctness of substitution where we have to give a sort of much fancier precondition and a much fancier postcondition. And the precondition basically is what the correctness assertion, it says that, assuming that x and the thing we're substituting have the same semantics, that's the precondition. The postcondition of our substitution operator says, well, if the postcondition, if our analysis asserted that x and ax were unmodified, well, that better be true. So this is basically claiming that, well, when our analysis told us the things weren't modified, indeed they weren't. So x was not modified. So the postcondition here is about the two states that we end up after substitution. So this is saying that, well, x hasn't been modified. This is saying that ax hasn't been modified. And in fact, the substitution invariant still holds, so they're still equivalent to each other in the resulting memory. So this is, a bit of work. And because imp is deterministic, we can also assert that the memories are the same. And then we need to do a little bit of relational reasoning to prove that this is actually a reflexive relation and that there's sort of a monotonicity constraint that just says that our analysis, if whenever we do a substitution in some state and our analysis says that ax was modified, well, it's going to be modified in the other state as well. So we need a little bit of work. So those are only needed in the proof. But the final thing we can get out of this is that if we take some command C and we substitute x for ax in it, and we get some substituted command C prime and a Boolean flag that tells us whether this was good or bad, then we can prove that, well, if we start in a state where the substitution invariant holds, then C is related to C prime under the postcondition, which is this complicated spec that just says, well, the values didn't change. And the consequence of that is basically this substitution is correct. And we can now rewrite C to C prime and use this postcondition to kind of connect the semantics together. So as a particular instance of it, one easy case is where we're substituting a for x. If a doesn't contain x at all, so that's going to make it easier to make sure that there's no sort of interference in the substitution operator. Well, then we can substitute through C, and in fact, we can relate the memory. This is sort of the memory where we've already assumed that x maps to the evaluation of a. In the precondition, this is going to be the same in the postcondition here. So this is basically showing that our substitution operation works correctly for these commands. All right, and with all of that, why did I go through all of that work? Well, I wanted to implement like a constant propagation, which is basically a kind of substitution operation. And so here is the syntactic program transformation that takes a command and produces a command. So this is a compiler optimization. And what does it do? Well, it walks over the command, and in the case where we have a sequence where we have an assignment, y gets a, followed by some more commands, well, we constant propagate the continuation C2, and then we do a little bit of work to say, well, if a contains y, we better not substitute because we're mutating the value of y here. That's going to change the meaning of the program. But if not, then what we can do, so we leave the program alone here, but otherwise we can actually substitute a for y in the continuation. So this is constant propagation. It would let us replace y equals z plus 3. If we use y later, we could replace all those occurrences by z plus 3, for instance. And then this is just folding over the rest of the program. This is actually just crawling over the whole problem. The only interesting case is this assignment, because we're sort of propagating this assignment later in the program. And finally, so as an example, if we apply that constant propagation algorithm to this piece of code, which is kind of needlessly complicated, we can see that, well, x gets 4 plus 5, and then we mention x here, and then we use x and y here, and so on. So if we do that constant propagation on this code, we end up with this. X gets 9, y gets 9, y gets 9 again, because we've kind of constant propagated 9 to here, and then we actually can do this entire if then else statically. So we'll get y gets 9 again, and then in any event, this is sort of a sound substitution, and it did a bunch of inlining and simplification. And we can prove that this is correct using that lemma. So it's not too difficult. So this is how you prove some compiler optimization correct in this style. And we can go further. I'm not going to go through loop unrolling. Actually, loop unrolling turns out to be a bit easier than constant propagation because of the I-tree semantics. It's like we already had an equational theory that had to do with unrolling loops. This is the loop unrolling as an operation on syntax, right? And it just does loop unrolling to some amount everywhere. And you can prove that it's sound by using the equational theory for loops that we already established. And finally, in a real compiler, you might do a bunch of optimizations and do them over and over again to expose more possibilities. And so this is really just it takes a optimization pass, you can think of it, which is a function from command syntax to command syntax, and runs n iterations of that optimization pass. And so this is completely generic, and we can prove a sound version. So for any syntactic program transformation, if we can prove that C is equivalent to opt-C, well, then it's very easy to show that if you run that optimization n times, it's still sound. And so finally putting that all together, we can get to, well, this is just setting up that factorial code with some examples. And finally, we can prove that the factorial command that we started with in imp is equivalent to the optimized version of it. And the proof actually is just this. So it's just unfold the definition and then use our sound optimizer. And then to go from, so that's loop unrolling and constant propagation. And then we need to, you saw from back here, this example introduced a lot of sort of dead stores, right? This store to y is going to be overridden by that one, and that's going to be overridden, and so on. So classic optimization is some kind of dead store elimination. And again, we can implement that. And I'm not going to, you can check out the Coq development for those things because it's not too complicated given what we've seen, but ultimately, right, what we can prove is given this syntactic representation of an imp command, it's equivalent semantically to this. And again, the proof is really, we do a bunch of optimization, we rewrite with our dead store elimination pass, and then that happens to leave one extra skip at the end. And so this is the correctness of sort of a fairly interesting compiler pass for imp. Good, so I have about 25 minutes left, and my plan is actually to shift to talking about Vellum and sort of how these things scale up. But before I do that, are there any questions about this stuff? So I know it's kind of a lot, and especially these logical, like, how did I come up with the post conditions for this? Well, one way you can do it is just try to do the proof and then think about what information you need to make it correct, and then you can kind of strengthen your invariance to get that to go through. But you can kind of step through the Coq development if you want to get more insight. Yeah, question. Yeah, so the question is, does this kind of scale towards separation logic? Yes, although for imp, there's not really a good use of separation logic because there aren't any, the heap is so flat and there's no interesting data structures, there's no pointers, there's sort of the memory model is too simplistic for something like separation logic to make sense for imp. But when you move to something like our LLVM semantics, definitely. And in fact, my recent PhD student, Irene Yoon, her dissertation has a kind of a IRIS-style separation logic built on top of these I-tree semantics in kind of the way that I've showed here. It's just that the memory model is much more complicated, and so the predicates you can write are, these. Here we had mem arrow prop, but the mem is so unstructured, there aren't any interesting predicates you can write. So for separation logic, you would want to have pointers and a more complicated notion of heap and that sort of thing. But yeah, it does work for separation logic as well. Great. Good. So let me switch. This is kind of changing gears a little bit. But I just wanted to give you a taste of how we kind of scale this up in this verified LLVM project that I've been working on for many years now. Just as a show of hands, how many of you are a little bit familiar with LLVM? Okay, almost everyone. Good. So I'm going to skip through that, and we have 20 minutes, so I'll try to get to the more interesting bits quickly. And this, I want to really, again, thank the many collaborators I've had for this. This is not a small project. And in particular, Irene and Yannick contributed to this specific part a lot. So most of you know what LLVM is, right? It's this intermediate representation that has lots of different source front ends and produces lots of different compiler back ends. But for the purposes of what our aim is really just the intermediate representation itself, right? So there's this language that looks like this. So for those of you who maybe haven't seen LLVM before, the code looks sort of, so here is a factorial function written in kind of standard C. If you compile this sort of naively without many optimizations, you end up something like this. So just to kind of orient you, right, this LLVM is made up of kind of basic blocks here, start and then an end. And it has a bunch of simple instructions, like you can allocate an address on the stack, you can do arithmetic, you can have branches and so on. It's a kind of very classic SSA style intermediate representation. And what we, so this is just kind of pointing it out. We have these control flow graphs with interesting branching structure, terminators. Technically, it's in what's called SSA form, which means that if you look at static single assignment, so if you look at the left-hand sides of these sort of instructions, N2, for instance, will only appear once on the left-hand side. So it's sort of you can think of these more as like lets or pure lets as opposed to mutable variables. And it has a lot of other features that make it quite complicated to reason about. So structured data, pointers, the memory model is quite complicated. There are a bunch of unsafe, so it has types, but mostly they're used for the same reason that C has types. It's to figure out the sizes of things in memory. And so it has a lot of unsafe primitives and undefined behaviors, and even some compiler representations for things like poison values that are sort of deferred undefined behavior. If you try to touch them, then you get your program explodes. So this is great. It's fairly complicated. This is when I'm trying to sell LLVM to other people, but it's amusing, right? This is the table of contents for the reference manual, which is big. And just to give you one example of things that are a little bit complicated, I always like to point to undef as a concept. So LLVM really, as an intermediate representation, I like to think of it, it's not really a programming language. It's more like the specification of a family of programming languages, because the semantics is actually quite non-deterministic. And so, for instance, one manifestation of that is this notion of undef. So you can think of it as like a value that represents a non-deterministic choice of bits for a particular bit size. And it's used for things like uninitialized registers or loads from volatile memory, that sort of thing. Right, so often it's used for things like loop invariant code motion. So you would like to hoist, so before this loop, X might be undefined. And then you might define it in the loop. And so you can, if you can show that, X is undefined around this loop, well, you could pick it, the compiler could refine this program by picking a very good choice of this undef value, which happens to be 0. And so this long computation can be eliminated by the optimizer. So the presence of undef is justified by the compiler implementers because it lets them be very aggressive in their optimizations. But it also makes things extremely complicated to reason about. So there are a lot of bugs that crop up. And here's a weird, unintuitive thing. So here are two undef. So these are I8s. That's the type of bytes, so integer, 8-bit integers. So if we OR an 8-bit undef value with 1 and then XOR it with itself, what do you think Y should be? 0. Yes, that's the plausible answer, and most people would think that is the right answer. But that's actually not LLVM semantics. It's undef is treated kind of lazily. So in particular, they'll substitute undef for X, or in this case, undef or 1 for X twice. And if you work out the semantics in that case, well, here we have sort of a set of possible values for undef. The meaning of the constant 1 is 1. But if we sort of substitute, if we take X to be the OR of 1 with undef, we get actually all odd bytes. So, and then if we substitute those kind of point-wise for the two uses, then actually, according to LLVM semantics, Y could be any even number. And then if you branched on, is Y equal to 2, it would actually, be allowed to pick that as a choice. So this is complicated and it interacts with optimizations. So a standard optimization is sort of strength reduction where you replace, say, multiplies by adds or shifts or something like that. But those are now only sound if you know that certain, you have to reason about undef. So this multiplication up there, if X happens to be undef, will give you even numbers. Whereas if X happens to be undef here because we've copied it, it can be anything. So this is really frustrating and a source of a lot of complexity of LLVM. They've been various times they're trying to move away from this semantics because it's really not very desirable, but they haven't yet. And for many years, this is what they want. And so we have to be careful. And if you go look at the LLVM semantics, there's lots of other complicated features. So and if you go look at the bug tracker, you can find John Reger's C. Smith and YARPGen projects have found lots of bugs related to things like undef. So here, I don't think it's fixable under the current undef. You have wrong code compilation errors because of these sort of semantic things. If we want to give up on some undef transformations, we have to really think about these. Here's John Reger. There are many optimization failures because different parts of the compiler sort of make different assumptions about, say, how undef behaves. OK, so what we're trying to do in Vellum is basically give a semantics, a formal semantics to LLVM IR. What is that semantics? Well, it's basically a set of possible executions for any LLVM program that is trying to, agree with the informal standard and at least meet the implementation. And we hope to do this by building essentially a semantics in Coq of the style that I showed you for IMP, but of course much more complicated. And then we can use it for things like verified optimizations and testing and that sort of thing. And so just to kind of paint the picture here, what we have in Vellum is like a thin OCaml parser and pretty printer shim layer that lets us take the .ll format, which is one of the human readable formats for LLVM IR, and put it into, ingest it into Coq as abstract syntax. And then we can do things like implement program transformations in Coq, prove that they are correct with respect to the semantics, and then extract an executable version of that optimization that you could kind of plug into the real LLVM pipeline. So this, unlike, say, ComCert, this doesn't give us end-to-end verification because we haven't verified the front end and we haven't verified the back end. Obviously, that would be interesting. But still, kind of just nailing down a spec for LLVM itself is interesting and quite hard. OK, so question is, how do we give a semantics? And here are a few things. So SSA is basically like functional programming, except of course, we have all these undef values and side effects. There's this complicated memory model. I should say also, we haven't considered concurrency yet in our semantics because that adds a whole other layer of complication. And there are actually several papers about LLVM concurrency semantics. It's quite difficult. But basically, the approach we take is literally writing these iTree-style layered monadic interpreters in Coq. So just to give you a sense of what that looks like, we have some algebraic data types for the syntax. So here, we have instructions like load and store and add, and we have basically code blocks just as syntax. And essentially, we interpret them first into interaction trees. And then we have lots of different types of effects, lots of different types of events that we handle in layers. So this is kind of pictorially you've seen several lectures about iTrees, but when I normally give this sort of a bridge talk, this is sort of a sketch, right? So if we have a load followed by an add and then a store, we have load and store events in our iTrees. So one interesting thing is kind of deciding what are the events in our iTrees. And of course, we just went through, this is if we have an infinite loop, well, this one would have a whole infinite series of loads and stores, and we would need to interpret those events into our memory model. OK, so this is iTrees. I'm not going to go over all that. What I want to get to is, this is we have an interpreter for iTrees, so we can sort of crunch down a tree like this into one of these memory state monads. So we do that in layers. And here's how we do it. So we have sort of a core IR. That includes things like these local variables like X and Y, the registers of LLVM. We treat that as one layer of effects. We have global variables are another layer of effects. The memory model is another layer. Undefined behaviors. The undef non-determinism ends up as being other events and so on. And so just as an example, we were seeing a very primitive type of memory events for IMP. But for LLVM, we have sort of alloca, load. And here, these types are LLVM types. So we have load, store. You can push a stack frame. You can pop a stack frame, and so on. Here, these types, U values, that's our internal terminology for the symbolic values that might involve undef. Because as we saw, if you have undef or 1, you sort of have to treat that as a set of values. And so That's what this U value thing is. And you can see that the result of reading from memory, the result of loading from memory, it will have to treat this U value as some kind of address in memory, and then it might produce a value that's loaded. And so that's one piece of the memory model. But as I said, we actually have lots of layers of these monadic interpreters. So we start with syntax, and here you can see the types of the I trees involved. So E0 is sort of all of the events that might happen in an LLVM program. And then I didn't bother to name them explicitly, but you can see that we have a global environment, a local environment, the stack in the memory, undef and non-determinism, undefined behavior, out of memory events. And then we even have some events that we treat as OS calls, so things like putS, so you can do IO. And so this picture on the left here, or on the right, is showing the stack of subsequently interpreted layers of our monad. And you can see we are introducing state T, and this is a little bit simplified, of course, but in some sense, so here when we interpret the global environment, we move into a state monad where there's a global environment, and we've handled the state. Here we've handled the local environment and so on. One interesting thing that is useful for our Vellum projects that I didn't really mention for iTrees is we can interpret we can interpret iTrees into any monad that supports iteration. One that we can use is propositional monad. So any function into prop in Coq is a monad and supports iteration. And we use that, so we think of this left path here as the actual specification. It uses logical predicates to say what is the non-deterministic set of allowed behaviors. For instance, when you allocate in the memory model, it will non-deterministically pick using an existential quantifier in Coq to say what address gets returned, subject to some constraints. This right-hand side is an executable version that would have to implement, say, the memory allocator, right? So on the left-hand side, we say allocating a stack slot could return any of these possible memory locations. We can have an algorithm that picks a particular one, and that's going to be executable, and we can run it as an extracted program. And so we sort of here's where we're taking advantage of having two interpretations for the same effects, same events. We interpret one, on the one hand, we interpret them as a spec. On the other hand, we interpret them as an implementation. Right. Right, so this is these layers. And what do we do with it? Well, we're interested in finding bugs both in our spec and in actual Clang. Because we have an executable model, we can run test cases using tools like CSmith, which can generate C programs that we can compile to LLVM. We've done verified program transformations and so on. And I thought I may as well show you a demo briefly, if I can. Is that big enough? So here, I have to look in two directions. So, for example, here is a factorial LLVM program. This is pretty close to the one that I showed you in the slide. You can see it's a loop. And there's a main here that just calls factorial of 5. And one of the things we can do is run our Vellum semantics as an interpreter. Right, and it will happily go off, implement all that memory model, and in this case, we'll get 5 factorial, which is 120. We could, we have lots of test cases. So you can see that's actually reasonably efficient for being able to test our semantics, and we can, run lots of programs. So really what's going on here is we have our Vellum interpreter, which is this, 7 layers of monadic interpreters, including a full memory model. And when we call the interpreter, we're using that full stack of handlers to simulate the memory, in this case, there's some allocation, there's some loads and stores and so on. We could also look at, for example, the recursive version of factorial, which is a little bit smaller. This is recursively calling factorial in the classic sort of way. Oh, it also implements factorial. So if we run this one, well, we're going to get the same answer, but we get it in a different way because we're doing recursion instead of iteration. So you can get a pretty nice semantics that we can run and play with, and we've found lots of bugs. And our hope is, we've used this to prove various optimizations correct. Over the years, we've looked at different kinds. But roughly, the idea is this kind of behavioral refinement of the kind that I was showing you in IMP, but much more complicated because we have non-determinism. But one thing we get out of this sort of way of structuring things nearly for free, although there's a bit of work, is that this side is sort of the propositional spec. Here we have an executable implementation of the spec. If we show that for every handler we implement behavior executably on this side, it's allowed by the spec, then sort of the monadic composition lets us prove that the executable we get out at least is an allowed behavior by the specification, more or less for free. So we get it just by kind of instantiating these refinement relations on both sides. So that's one of the nice things, and then we can do lots of different optimizations. So it turns out that because of the complexities of the LLVM memory model, even really seemingly trivial program optimizations like this one, where we allocate an unused stack slot, do a pointer, this should be pointer to int. There should be PTR, I missed it there, and then return void. So in some sense, we allocate a stack slot, cast it to an integer, cast the resulting pointer to an integer, and then ignore it. It turns out this refinement is surprisingly hard to prove in memory models. And so that's one of the more interesting problems we've been working on lately, and we have some work coming out about this. Happy to talk more about that. I mentioned my student Irene's separation logic version. So we have, she did a lot of work to put iTree semantics into Iris, and then we can use Iris support for separation logic justified in the same way that I showed you for the Hoare logic, of course, more complicated. But you can then prove things like this kind of loop invariant code motion using separation logic to prove these kind of optimizations correct. OK, good. So I think that's a good place to end about Vellum. I'm happy to talk more about that. I realize it was a very whirlwind tour, but maybe let me just conclude. So let me switch back to my other presentation mode. I did this and go over to further. What I've been talking about is sort of using monads and relational reasoning to implement interesting semantics in Coq. If you're interested, you can take a look at the original iTree's development. There's a tutorial there that goes through a compiler from IMP to a kind of assembly language and shows you how to kind of set up the refinement proof to do a more interesting compilation. And this is kind of interesting because we have just the memory events on the iTree side, and we have registers and memory on the compiler side. And so being able to line things up with different handlers on different sides is quite interesting. Here, we eventually prove this kind of relational postcondition that just says that the memories are the same on both sides after you run the programs. I just went through Vellum. You can find that also on GitHub, and we recently did an OPAM release, so if you want to install it that way, you can. And there's a lot of open questions and further work. So we have iTrees are kind of fun. There have been a lot of things that have been built on top of that. If you're interested in non-determinism, we have some further work on something called choice trees I mentioned a bit earlier today. All of this is, of course, connected to things like free monads and algebraic effects. If you want to get deeper into monadic reasoning, there's a very nice work on what are called Dijkstra monads. And we have some papers that connect I-tree semantics to those, and some reasoning about these monadic interpreters. This general idea of relational reasoning is very powerful, and a very nice paper kind of summarizes the intuitions and shows you how you can do it, is by Nick Benton from Popple 2004. That's a very good entry point to a lot of that. But you can also read, the next 700 relational program logics. And I didn't really get much into co-induction, but a lot of people had questions about co-induction on the Slack. These are a couple of good starting points there. Oops, this should be all the way up, not all the QA up. But basically read everything by Damien Poust. He's got some nice Coq libraries and explanations of co-induction. So I hope you enjoyed it, and I'm happy to take any questions. Thanks.